Next, we will see the potential due to charged sphere, that is solid sphere. That means inside the sphere you have charge. So that means it has a volume charge density. So if Q is a charge, then I can write rho V equal to charge per unit volume. From that, Q is equal to V into rho V, that is equal to 4 by 3 pi capital R cube rho V. This is the charge of your solid sphere. Now we will take a point P at a distance R from the sphere. Then I can write dV is equal to minus AdR. This we know. Now the point to be noted is from this step only we will start the derivation for our V for the point P, which is R distance away from the center. Okay. From this step only we start the derivation. This equation is the general equation of charge for a solid sphere. Q is equal to 4 by 3 pi capital R cube rho V. Okay. Dou V equals minus E dr. Okay. And you know what is E? E is equal to Q by 4 pi epsilon 0 R square. That I am substituting here. That into dr. I am integrating it. So finally I will get V equal to Q by 4 pi epsilon 0 R, and that V is my V outside. Okay. Now case 2. This is a point P on the surface. You can see if this P is placed here, then what happens? The only difference is small r becomes capital R. So I can rewrite the expression as Vs equals Q by 4 pi epsilon 0 capital R. Now I am taking a point P inside my solid sphere, which is at a distance R from the center. Again I am writing dV equals minus A dr, where this E is the electric field intensity inside my solid sphere, and this formula for E inside we have already derived using Gauss law for solid sphere, that is E inside is equal to R into rho V by 3 epsilon 0. Okay, that I am substituting in this E. Okay, so substitute 2 in 1, I will get dV equals minus R rho V by 3 epsilon 0 dr. Then I am integrating. That is integral dV equals minus integral R rho V by 3 epsilon 0 dr. Okay. Now since I am integrating, I have to put the limit also. So integral dV, the limit is from this point, this R point, to my surface. Okay. From this point to this point is my integral. Okay, is it clear? So this is my surface, so that is Vs, and this is my V small r. Okay, that is written here. The limit will be Vr to Vs, and here the limit of r will be from small r. This is my small r, and towards the surface the r value is capital R. Okay, so the limit is small r to capital R. Then I am integrating. V equal to minus rho V 3 epsilon 0 is taken outside. Then R dr is integrated. I will integrate it. Then I will get R square by 2. I am putting the limit here. So finally I will get Vs minus Vr is equal to minus rho V by 3 epsilon 0 into capital R square by 2 minus small r square by 2. Then we know what is Vs. Vs is equal to Q by 4 pi epsilon 0 capital R. That I am substituting in equation 3. Okay, I am substituting in equation 3. Vs is equal to 1 by 4 pi epsilon 0 Q by R. Now before substituting Vs in equation 3, what I am doing is, listen here, Vs is equal to 1 by 4 pi epsilon 0 Q by R. This Q we have already derived, right? This one. This Q is equal to 4 by 3 pi R cube into rho V, right? That Q I am substituting in my equation 4. We know already Vs is equal to 1 by 4 pi epsilon 0 QR, and in that Q I am writing 4 by 3, this one 4 by 3 pi capital R cube rho V. Okay, rho V. Then I will get my Vs is equal to R square rho V by 3 epsilon 0. Then that Vs is substituted in equation 3. Clear? That Vs is substituted in equation 3. You substitute it, rearrange it. Finally, I will get V small r is equal to rho V capital R square by 2 epsilon 0 minus rho V small r square by 6 epsilon 0. This step I am not explaining because just mere some rearrangement and all. So this is my final expression, small Vr, that is the expression for the potential at this point P, which is at a distance of small r from the center. Okay, that is my V inside. Vr is equal to rho V capital R square by 2 epsilon 0 minus rho V small r square by 6 epsilon 0. Okay, now go through these derivation, and if any doubt please ask me. Okay, now as self study you have to do potential due to, you have to find the expression for potential due to infinite line charge. Okay, then there is one more topic in this section, that is equipotential surface. A surface on which the electric potential V is constant throughout is said to be a equipotential surface. Example is the surface of a charged conductor. Earlier I told you that across a charged conductor the electric field is uniform. So if the electric field is uniform, the electric field intensity is uniform, so V also will be a constant. Okay, our another example is any sphere with a point charge at its center. These are the examples for equipotential surface where the potential V will remain constant throughout. And another topic for self-study is features of equipotential surface. That also you can do by yourself. Okay. Then there are few problems worked out here that we will see in the next class. Till then, good day. Thank you.